Okay, thank you for the invitation and the introduction. Okay, a bit too close. Okay, so the plan for this, so I hope that these 3 talks will be very easy. So all the objects that I'm going to talk about are familiar to most of you. So these will be hopefully very easy 3 talks. And the plan is, so first I'll talk about Deline's construction of local epsilon factors. Well, I won't give the construction, but I'll just recall sort of main properties and so on that I need for the second and third talk basically. In the second talk, I'll give a formulation of the what Kato calls non-commutative local Tamagawa number conjecture. So it basically sort of roughly says that these epsilon factors of Deline come in a family as well, just like the L values do. And so I'll give the formulation of this conjecture in the second talk. And in the third talk, I'll give a proof of this conjecture in the L not equal to P case. So whatever that means, I guess that will be clear tomorrow. Okay, so I should also sort of quickly add that there is a proof of this conjecture by Yasuda. He was very kind to give me a preprint of his paper, but this proof will be very different. So his proof is much more involved and probably gives something, I don't know, maybe gives something more, but this will be quite simple. Okay, so let me start with some very basic things. So virtual representations of a group, because I need this both today for what Deline does and then again in my third talk. So this, as most of you may be aware, there's this unpublished long paper of Langland's in which he constructs epsilon factors, sort of purely locally, I guess, local epsilon factors purely locally. And what I'm going to do about Kato's conjecture will be somehow similar to that. Of course, that I'm not claiming that it's purely local or anything, but Langland sort of gives this description of Bravas, the kernel of Bravas induction map, which I'll say again more, and somehow I'm doing the dual of that in my third talk. Okay, so I'll need all these objects anyways. So K is any field for now of characteristic 0. G is any group. And I denote by RKG the Grothendieck group of so K0 of KG modules which are finite dimensional K vector spaces. Okay, so G can be infinite. That's why I need to put this condition. So you can easily see that this is this is free abelian group on isomorphism, phi abelian group on, isomorphism classes of irreducible K representations of G. Okay, finite dimensional K representations of G. So you take all the finite dimensional K representations of G and take the free abelian group generated by it. That's same as this K0. Okay, so let me just sort of write down something. So this is, you must have seen all this in your representation theory course, but RKG is a ring with product given by tensor product, and then there are some natural isomorphisms from RKG to various other groups or rings with product given by tensor product over K. Okay, so I'll use this as well. Okay, so examples of some homomorphisms from RKG. So first one that's very useful for us is the dimension. So this is from, okay, so you just take dimension as K vector space. It's one ring homomorphism that will be useful. I think we also need determinant. So okay, so this is just a group homomorphism. If H is a finite index subgroup of G, then we get a induction map from RKH to RKG. Okay, so
just map on RKG star.
this one. Ah, right. Yeah, sorry. Otherwise, can't I do this?
Okay, yeah.
Yeah, okay. I mean, okay, but thanks. So, H is a finite index subgroup. Okay, and then I need the restriction map from G to H. So this is so H is any subgroup. Okay, in this case. Okay, so I need what is called Bravas induction theorem for groups. So let me write this down. Okay, so let me state this. So I'll just state it for finite groups, but I'll later use it for profinite groups. Maybe I'll say a word about it later. Anyway, so I first have to define elementary groups. So let P be a prime. A finite group G is called PK elementary if it is of the form if G is C direct some P where P is a P group. C is a cyclic group of order n. So C is isomorphic to Z mod nz, and P does not divide n. And image of this map, which goes from P to automorphisms of C, which is Z mod nz cross. This is contained in Galois group of K zeta n over K. Okay, so I am identifying the cyclic group C as being generated by this root of unity. So most of you must have seen the definition of P elementary, and I'm just sort of putting in a K here, so you need this condition. So a group is called, so G is called K elementary if it is PK elementary for some prime P. Okay, and as an example, so what is usually called, so G is elementary if it is K elementary for algebraically closed field K, for K algebraically closed. Okay, so in this case G is just direct product of C and P. Okay, so what's the theorem that I want to state? It's got an old theorem. So all, by the way, I should have said somewhere. So elements of RKG are called virtual representations. So they are linear combinations, Z linear combination of representations. So I'll distinguish this by calling them virtual representations, actual representations and virtual representations. Okay, so I'll just state it maybe not in such a standard form. So again G is finite here, and then all virtual representations of all virtual K representations of G of dimension 0 are let me state it like this. I just get confused with the word. So any virtual representations of G of dimension 0 is a sum of virtual representations induction from H to G of chi with chi a virtual representation of virtual K representation of H of dimension 0 and chi is a linear combination. I'll also state it in a slightly different form, which is easier to understand, I think. Linear combination of dimension 1 representations of H. Okay, so everything is K representation. So dimension 1 K representation. So let me quickly state the different form that yeah.
Chi could be a one-dimensional representation.
Yeah, but I want it to be of dimension 0, so you could take chi minus 1. Yeah, because. But yeah, I'll state it in that form now. So let Rk plus G be the free abelian group sorry, I should say here, and H is K elementary. Yeah, so everything can be induced from K elementary. That's why I made this definition. The free abelian group generated by pairs H and chi, where H is a subgroup of G and chi is a one-dimensional representation of H. Okay, so I can define a map from Rk plus, so everything is K, to Rkg, which takes this pair to the induced representation, and then Bravas theorem just says that is surjective. In fact, I mean, you can also, so this is the way I've stated it here, it's all subgroups H and then one-dimensional representation of H, but in fact you can just restrict it to K elementary and it's still surjective. Okay. So why is this theorem useful? It's because if you want to know something about, so if you have a map from Rkg to any other ring or whatever, and you know how this map behaves, so for every group you have this map, and you know how this map behaves under induction, then you have to know about this map only on one-dimensional representations of elementary groups somehow. Okay, so that's the nice thing about this. So this, we'll use this in twice in what you're doing. So this concludes the first part of my talk about group sort of representations of groups, profinite groups or finite groups. Then the next thing is I want to say something about the local epsilon factors, but only for one-dimensional representation. So this is already in, I think the best place to read is Tate's thesis for this. Or in fact, Kevin Buzzard has a huge notes about the teaching about some course he was giving in London on Tate's thesis. So maybe that's a good place to read also, but I haven't looked at it carefully. So let me just define the local Weyl group. So now K is a local field. Let me just stick to characteristic 0 for these talks. Okay. So one case is K equal to C, and in this case this is the Weyl group. Where this acts by complex conjugation, and K is non-Archimedean, so some finite extension of QP. K bar is algebraic closure, chosen algebraic closure of K. Then of course there is this exact sequence with inertia group and Galois group of K bar over K to Z hat, which is Galois group of the residue field. Okay, and the Weyl group is just inverse image of Z. So this Z contained in here in Galois group of K bar over K. Okay, it should be going here, right? And I put some topology on this to make it a topological group. Okay, so put a topology on this so that I is open in and has the usual topology. Galois group of K bar over K. So I has this topology coming from as a subspace of Galois group of K bar over K, and I just put another and I make it open in W K bar over K. Okay, so W K bar over K is not a profinite group at all. Okay, so what's the next thing I have to do? Maybe I have to. Okay, I won't talk about any. So let me just give you what the local L functions are, local L factors. Okay, so for each quasi-character or continuous homomorphism, chi from K cross, so K again as in third section is a local field of characteristic 0. We define the local L factor L chi as a complex number. Okay, so maybe infinity. Okay, so again I take the cases, so K equal to C. Then you can take it as an exercise if you haven't seen that any chi is of the form. So if I write Z in C cross as R e to the power I theta, then this chi of Z is so what's the notation I've used here? R to the S and e to the I theta n for some n in Z, and in this case, so again this is sort of Tate does this computation by defining them in a different way, but I'll just write down what the factor is. So this is 2 to the pi into 1 minus s plus mod n over 2 and then some gamma factor. Okay, so this is the usual gamma function. Okay, so this is the factor at complex place. So I think today's talk is just about sort of giving all the objects that we need for next two talks. Two is, so in this case again you can check that chi is either x going to mod x to the s or x going to sine of x mod x to the s. Okay, so in these two cases you define the L factor as again some gamma factor and some powers of p, or you can sort of look at Tate's thesis and see how it does the computation. So this defined in a different way. Okay, and the last case, this is easy here. So okay, so I'll say what this means if it's not clear a priori. So K is non-Archimedean, then L chi, this is equal to 1 if chi is ramified. Okay, and it's 1 minus chi pi inverse if chi is unramified. Okay, so here pi is a uniformizer of k or ok, whatever you want to. So ok is the ring of integers of k. Okay, so I just wanted to sort of give this definition of local L factors because this is quite easy and they work well with respect to induction and so on. And the epsilon factors which appear in the functional equation of these of L functions, global L functions, you think that somehow they should be easier, but their definition is much more subtle. So let me give a definition, I mean at least for general representations. Okay, so let me just give quickly the definition for quasi-characters. Of epsilon factors for so first of all I have to fix various things for to give this definition. First is I have to fix so psi is a non-trivial character of K. So again K is from the third section. Okay. So I have to fix this. Dx is a Haar measure on, so fixed one. We'll fix one later, but for now it's just a Haar measure on K. D cross x is a Haar measure on K cross. And then what you do is you take any C infinity function on K with compact support. With compact support. Okay, then so Tate defines the epsilon factors as follows, and he proves that it's independent of F and so on. So okay. Okay, so let me just define the Fourier transform for you first. So this is f of x psi. So okay, so what's the definition of epsilon factors? This is due to Tate and it's independent of F. But it depends on other things. So it's defined as this ratio. So you take integral f hat omega 1 chi inverse. I should say what omega s is, but I'll say this in a moment. So divided by the L factor of chi inverse omega 1. This is epsilon chi psi. So it depends on all these choices and multiplied by f of chi, I put x everywhere of course, divided by the, so here omega 1 or omega s is this which takes x to the valuation, the norm of x to the s. So I have to fix norm on all these fields, which I won't say. This is the usual thing that you would take. Okay, so this is the definition of these epsilon factors. Okay, local epsilon factors for quasi-characters. So if you take any chi, this is how you define it. And it's independent of f, but it depends on psi and dx. So that's why we put that in the notation. So let me write down a couple of properties of these, and then I'll state the theorem that Deligne proves. Okay, so firstly, what happens if you change the measure? If you scale it by something, you just scale your epsilon factor. And if you scale your character psi, then again, so this is a times something. So actually let me write psi a here, dx, this is chi a epsilon dx. So what is psi a of x? This is by definition psi of ax. Okay, so it's another additive, it's another character. Okay, so what's the theorem of Telein? And maybe I'll put Langlands' name in there, because the way I'll prove it is sort of somehow, so the way I'll prove Carter's conjecture is somehow what Langlands does as well. Okay, so what does this say? It says that there exists a unique function epsilon for each of this tuple. So for each tuple it gives you some value. So what's the tuple? You have k, you have fixed k algebraic closure, you have this choice of psi, you have this choice of dx and v. Okay, so all these objects I have said, I just have to say what v is. So v is a representation of okay, so representation on a finite dimensional complex vector space V. So continuous representation on a finite dimensional complex vector space V. Okay, so for each tuple I can give you a value of this function on each of these things such that it satisfies several properties. I'll write them down here. Okay, so right now we have these for one dimensional thing. Okay, so using the reciprocity map we have it for one dimensional representations of the Weyl group. Now we want to extend it to everything. So okay, and such that it's so for a short exact sequence 0 to v prime to v to so of representations of the Weyl group like this, you have epsilon, so v psi dx is product of these two, the numbers for v prime and okay. The second is if I so it's the corresponding of the first property. So if I have v psi a dx, this is a to the dimension of v times epsilon v psi dx. Okay, so in particular if dimension of v is actually I should yeah, so using 1 I can extend I mean once I have this theorem I can extend it to all virtual representations using 1, and then I can talk about the epsilon constants for dimension 0 representation. So in particular, if it's dimension 0, then the epsilon constant is independent of the measure you choose. Okay, so the third property somehow depends on this fact that if you have dimension 0, then it's independent of the measure you choose. So if L over K is a finite extension, and VL is a dimension 0 virtual representation of this subgroup of the Weyl group of K bar over K, then the epsilon constant for the induced representation. So these are properties like that of L functions. So VL of psi is same as the epsilon constant for VL, but now I have to choose a additive character on L. I choose the obvious one, so I take the trace first and then compose it with psi. And lastly, if dimension of so if V is a dimension 1 representation, so not a virtual representation but actual representation of K bar over K, then the epsilon factor for V agrees with chi dx, where chi is here. So this is chi and this is V. Automorphisms. Okay. So it sort of, in the one dimensional case, it agrees with what we have defined before. Okay, so let's see. I'll stop by making a remark about how Bravas induction theorem comes into this. So there exists at most one function epsilon, as in the theorem, by Bravas induction theorem. Okay, so as I said, I stated Bravas induction theorem for finite groups only, but so Weyl group has this okay. So you can twist your okay. So from representations of Z, you would by sending Frobenius to some power, you would get representations here, and you can inflate it to a representation of the Weyl group. So you can twist your representation by these one-dimensional things so that it becomes trivial on this part. So then it's just a representation of I, which has to continuous one, and I is profinite. So that has to factor through some finite quotient of I, and hence you can sort of apply Bravas induction even to this group. I'll say this more about this more in the third talk when I'm actually doing it sort of in the p-adic case. So I don't want to spend time now doing this, but you can apply Bravas induction in some form to this group, and then you have this third property which says that if you induce representations, then the epsilon, this function should behave well with respect to induction. So you can so Bravas and property 4 tells you what it is for one dimensional representation. So using 3 and 4 you can sort of see that Bravas induction theorem gives at most one function like this. So now so in fact Bravas theorem gives a candidate for epsilon, because we have this surjection. Okay, so now G is an appropriate quotient of the Weyl group. I won't say what. Okay, since we have this, provided we can prove that epsilon on the kernel of this map is trivial. Okay, so it's 1. And this is in general quite hard, because first of all it's not straightforward to compute what this kernel is, but actually Langlands does this in this infinitely long paper. This is how Langlands proves the theorem in his unpublished paper. So he in fact computes what so this is you can define a ring structure on this, because you know this theorem that you learn in representation theory, that induction, if you induce tensor product of two representation, you get sum of induced representation. So this is a ring homomorphism, using something like that, and so you can find generators of the ideal of the kernel, and that's what Langlands does for all finite groups. And then he actually goes on to show that on these generators of the ideal, epsilon factors are trivial. So this is very lengthy and quite tricky. On the other hand, what Deligne does is that he says that if you, there is a straightforward definition of global epsilon factors, and global epsilon factors satisfy all these properties very easily, because L functions satisfy them. And so he says that if you know that the epsilon factors if the local epsilon factors at all but one place behaves well, and because the global epsilon factors behave well, the remaining place should behave well with respect to induction. And then given any local extension, he comes up with an appropriate global extension where which gives you this local extension after completion, and at every other place it behaves well. So that's the sort of global argument that he uses to simplify the proof of this theorem. But Langlands actually does all the Langlands does the hard work of giving a local proof by computing what the kernel is. Okay, so what I'll do tomorrow is I'll give sort of more. I'll give so So this is, I won't prove this theorem at all, but in the one-dimensional case, I'll give explicit formulas for the local epsilon factors. I'll state what Kato's conjecture says, so this p-adic local conjecture, and how this is related to sort of finding the kernel here. How its proof is related to finding the kernel here. And then in the third talk, I'll actually sketch a proof of that Kato's conjecture. Yeah, okay, thanks.